It is quite common to be in situations or where we want to test hypotheses related to population proportions. And so we've collected some data from a population. It's going to be sort of a success-fail, a binary outcome of some sort. And we want to know what is the proportion in the population, but we're going to be relying on our sample proportions in order to do this. And if we want to test hypotheses related to proportions, and it comes up frequently enough, it's good to have a procedure that we can follow in this situation so that we don't need to work with the general framework of hypothesis testing, so that we can turn towards a specific hypothesis test. And in the case that we have a large enough sample, what we're going to be able to do is make use of z-tests or normal-based tests for population proportions. And ultimately, this is going to be justified by using the normal approximation to the binomial distribution, which is justified anytime that you have a large enough sample size there. So in order for us to test hypotheses relating to population proportions, we can use the z-test or the normal-based test, invoking the normal approximation to the binomial. So reviewing the normal approximation to the binomial, right, if x follows a binomial NP distribution, then x counts up the number of successes in n independent trials where each trial has a probability of success of p. So the sort of standard example for a binomial distribution is going to be the case of flipping a coin over and over and counting up how many heads did we get on that coin, right? And so sort of what we're thinking about. X is counting up the number of heads. From a binomial distribution, we know that the expected value is always equal to n times p. N is the number of successes, p is the proportion of successes or the probability of success. The variance is always going to be n times p times 1 minus p. If we take n to be large enough, at least large enough relative to the values of p and 1 minus p, then we know that x is going to be approximately normally distributed. And this comes from the normal approximation to the binomial. Now, the rule of thumb is that we are going to take n times p greater than or equal to 5 and n times 1 minus p to be greater than or equal to 5. But again, this is a rule of thumb. If it's close, then it might work. If it's, way larger than 5, you're probably going to be fine, right? So it's essentially you need a large enough n, and that's sort of a good rule of thumb here. Once we have that approximation that we're willing to make, then we can say that x is going to be approximately normally distributed, and that's going to be with a mean of n times p and a variance of n times p times 1 minus p. So the mean and the variance of x to begin. Now, if we form the sample proportion, the way that we take this is by taking x and dividing it by n, right? So if we know that we saw 5 heads and we tossed a coin 10 times, then the proportion is 5 out of 10, right? Or 50% in that case. And so because the proportion just comes from scaling up or down x by a factor of n, then we know that the proportion is also going to be approximately normally distributed. And specifically, it's going to have a normal distribution with a mean of p and a variance of p times 1 minus p divided by n, right? And so in this case, because this proportion is approximately normally distributed, then we can use a z-test here, or a normal-based hypothesis test, right? So the z-test can then be used for the population proportions. This is going to be an approximation, and it's based on the normal approximation to the binomial. So how does the z-test actually work when we're dealing with population proportions? So first, we need to see that n is large enough so that we can actually apply the z-test. And then from there, we're going to be working on our z-score test statistic, right? So the z-score is going to take the population or the sample proportion, subtract off the proportion under the null, and then divide by the standard deviation, right? So this is our standardization procedure that we're used to using in normal calculations. Right? Under the null hypothesis, we know that the true proportion is p naught, right? And so then p naught gets filled in for p. The variance is p times 1 minus p over n. And so then here we're going to fill in p naught times 1 minus p naught divided by n, square root that because we need the standard deviation, not the variance, right? If we have the null hypothesis that p equals p naught, then z here is going to follow a normal 0, 1 null distribution. Okay, so from that point, we can use normal probabilities in order to calculate our p-values, or we can use normal critical values in order to draw conclusions for our hypothesis test. The same z-scores are going to apply if we want to test the one-tail test as well. So p is less than or equal to p naught, or p is greater than or equal to p naught. All of them will use the same z-values. Right, and so with our z-score, with our null distribution, we need to figure out what our p-values or our critical values are going to be, right? So in order to do this, we're going to make use of the normal distribution. Right, so if we first consider the two-tail alternative, the null p equals p naught versus the alternative of not being equal, we're looking at an alpha level of significance, right? Then if we want our p-value and we've observed z is equal to z, we want to know what's the probability that z is less than the negative version or that z is greater than the positive version. Because this is a normal distribution, we can use phi, right? So it's going to be phi of the negative plus 1 minus phi of the positive. The symmetry of this ends up working out that this is 2 times the negative version here, right? So that's how we can get our p-value in the two-tail case. For the critical values, we're going to be looking at our z critical value. So we'll have alpha over 2 and 1 minus alpha over 2. Because of the symmetry of the normal distribution, we know that z alpha over 2 is equal to negative z of 1 minus alpha over 2, right? And so we really only need to look at the one critical value. The other critical value is going to be the negative version of that. If we instead are considering the lower tail alternative, so that the null is that it's greater than or equal to, and we're looking at an alpha level of significance, right? Then if we want the p-value, we just want to know, well, what's the probability that we observe something less than what it is that we actually observed? This is given by phi of what we have observed here. The lower tail critical value is just going to be z alpha, right? Remember that we have z alpha over 2 for our two-tailed test. We're only using z alpha here, and that's because in the two-tail test we have to divide that alpha over 2 into both of the tails, whereas in this case we're only looking at the lower tail value. Okay. In the upper tail case, we're going to be looking at much the same thing. So if we have the null is that it's less than or equal to this at the level of significance, then our p-value is going to be, well, what's the probability that we observe something that is greater than what we actually observed, which is given by 1 minus phi of the observed value. The critical value is going to be the z 1 minus alpha critical value. And once again, this compares to the z1 minus alpha over 2 in the two-tail test, where that alpha over 2 gets distributed on both tails, whereas here we only need the single tail, right? So we can use these z scores, calculate our p-value or our critical value, and then draw the conclusions according to the standard rules of hypothesis testing. Okay. It's worth taking a look at a couple of examples here. To make sure that this Z test for proportions makes some level of sense. All right, so here we're dealing with a pharmaceutical company. They claim that their new drug is effective in treating a specific disease, 80% of cases. A clinical trial is conducted on 500 patients, and 420 of them show improvement. Right, so we want to test the hypothesis at the 0.01 level of significance here. And so what are we actually given here? Well, the first thing to note is that we are making a claim, right? So the claim is going to be that the proportion of successful treatments is equal to 80%, and that's going to be treated versus the alternative that p is not equal to 80%. So we're dealing with a two-tail alternative here, right? We run a trial. We have n is equal to 500 individuals. We have x being equal to 420, right? And so then p hat in our case is going to be 420 over 500, which is 0.84. Okay, so we observe 84% in our sample actually show improvement. We want to test this at the alpha equals 0.01 level of significance. Now, here we would want to check n times p naught, and we'd want to check n times 1 minus p naught, and make sure that both of these are greater than or equal to 5, right? And in this case, n being 500, if you're looking at 500 times by 20%, or you're looking at 500 times 80%, both of those are going to be greater than 5, and so we're going to be fine to use the normal approximation here. And so then this works out to be, let's find our z-score, right? And our z-score is going to be given by the observed proportion, which is 0.84, minus the proportion under the null, 0.8, and then we have to divide this by the standard deviation under the null hypothesis, so that's 0.8 times 1 minus 0.8 divided by n. Right. And once we have that, we can then work out that our p-value is going to be 2 times by phi of negative z. Okay. And so that's the sort of general thought process. We can now work through sort of what the specific results actually happen to be. Okay. So we note first that the normal approximation is actually going to apply because n times p naught and n times 1 minus p naught are both greater than 5. We're wanting to test p equals 0.8 versus the alternative that p is not equal to 0.8. Right? We observe n is equal to 500, x is 420, and so that the proportion is 0.84. We calculate our z-score, right, 0.84 minus 0.8 over this estimated standard deviation, and that works out to be 2.236. Okay, so we can work out our p-value owing to the fact that this is a two-tailed alternative, right, as 2 times by phi of the negative. So that's 2 times phi of negative 2.236. In R, that is 2 times by p norm of negative 2.236. P norm in this case gives us phi. Right? So p norm of whatever is the same as phi of whatever. Okay, if you work this out, that gives us a p-value of 0.0254. Right, and so once we have our p-value, we can compare our p-value to the level of significance. We find that the p-value is larger than the level of significance, and as a result, we're going to fail to reject the null hypothesis in this case. So now we can actually draw this conclusion and communicate the results here. So since the p-value, which is 0.0254, is larger than the level of significance, we're going to fail to reject the null hypothesis at the 0.01 level of significance. As a result, we have insufficient evidence to contradict the claim that the drug is 80% or effective in 80% of people. The drug was effective for 84% of individuals in the sample, which is not significantly different from 80% at a 1% level of significance, right? So we did not reject the null hypothesis. Turns out that the claim that the company is making appears to be accurate. In this next example here, we have a school district who's claiming that the proportion of students meeting provincial standards is 75%. We take a random sample of 200 students and find that of those 200, 140 met the standards. We want to test the hypothesis of 0.05, and we want to use critical values in this case. Okay? And so in this case, we first identify, well, what is our hypothesis that we're testing, right? The claim is that the proportion of students meeting standards is 0.75. Right? That's going to be versus the alternative that p is not equal to 0.75. Right, we look at what observations we've observed. So n is 200, we have x is 140, right? And so then p hat is going to be equal to 140 over 200, okay? Then we can also consider, well, can we actually apply our z-test here, right? So we're going to need to take p naught times n, and we're going to need to take 1 minus p naught times by n, and we're going to check, are they both greater than 5? Okay. And then if they are, then we can apply our z-test here, right? So it's going to give us our z-score, and then we're going to compare that to critical values. In this case, we need 2 different critical values because of the fact that this is a two-tailed test, right? We have a two-tailed alternative up here, and so as a result, our z-scores are going to be z of alpha over 2. Our critical values are going to be z alpha over 2, and we'll compare the z-scores to those. So that's the general procedure that we're thinking about. Now we can fill in based on the values that we've actually observed here. Okay, so np naught and n times 1 minus p naught are both greater than 5, and so that is totally reasonable. We're testing the null that p is equal to 0.75 versus the alternative that p is not equal to 0.75. We observe n is equal to 200, x is 140, and so then that works out to p hat being 0.7. From here, we can actually work out the z-score, right? So we plug in the 0.7, which was our realized value, subtract off the value under the null hypothesis, divide by the standard deviation under the null hypothesis, right? 0.75 times 1 minus 0.75 divided by our sample size, everything square rooted. We work that this turns out to be negative 1.633. Okay, so now we want to figure out what our critical values are. Again, we're going to need the alpha over 2 critical value, right? So since it's a two-tailed test, we take z alpha over 2, which is going to be z of 0.05 over 2, which gives us our negative 1.96. If we wanted to find this using R, we can take our Q norm function. Q norm of 0.025 is going to give us that negative 1.96. And so then we can compare the results that we've observed to the critical value. Right, and we find that negative 1.633 is smaller in magnitude than the critical value, and as a result, there's not sufficient evidence to reject the null hypothesis here. Right, and so then we fail to reject the null hypothesis, and so we want to communicate this result. So since our z-score is smaller in magnitude than the critical value, we fail to reject the null hypothesis at the alpha equals 0.05 level of significance. As a result, there is insufficient evidence to contradict the claim that 75% of students meet standards. So in the sample, 70% of students met standards, which is not significantly different from 75% at our 5% level of significance. Okay. The third example that we're looking at here has a chemist, and they're hypothesizing that fewer than 5% of units of a particular compound have unacceptable levels of impurity. So they take a sample of 1,000 units of the compound and analyze them and find that 30 units are found to have impurity levels exceeding standards. They want to test the hypothesis at the 2% level of significance. And so what we're dealing with here is actually a one-tailed test, right? So their hypothesis is that fewer than 5% of samples have impurity levels, right? So they want to actually sort of show that the proportion is going to be p less than 0.05, right? Which is going to correspond to a null hypothesis of p greater than or equal to 0.05, okay? In this case, we're taking n to be 1,000. We're taking x to be 30. We have alpha equals to 0.02, okay? We need to first verify that n p naught is greater than or equal to 5, and that n 1 minus p naught is greater than or equal to 5, right? Assuming that those are both satisfied, which they are in this case, then we can work out our z-score. From our z-score, we need to find a p-value. And in this case, the p-value, because we are just looking at the lower tail alternative, is going to be the probability that z is less than or equal to what it is that we actually observed, right? Which is just going to be phi of the observed value. We can use r to calculate that value and then draw conclusions from there. Okay, so we can start filling in all of these results here. We note that the normal approximation is actually going to apply. So we're testing the null hypothesis that is greater than or equal to 0.05 versus the alternative that is less than 5%. We observe n is 1,000, x is 30, and so then p hat here is going to be 0.03. The z-score is calculated as 0.03 minus 0.05 divided by the standard deviation under the null hypothesis, which is 0.05 times 1 minus 0.05 over our sample size here, square rooted. We find that the z-score is negative 2.9, right? Because it's a lower tail, we take our p-value to be phi of negative 2.902, which we can find in R as p-norm of this, because the p-norm function gives us phi, right? And so taking that all together, we find that the p-value is 0.0019, right? 0.0019 is less than our level of significance of 0.02, and as a result, we're going to reject the null hypothesis, right? As a result of rejecting the null hypothesis, we do find, in fact, that fewer than 5% of samples have an unacceptable level of impurity. Right, so writing this out as an actual conclusion, since the p-value, which we found to be 0.0019, is smaller than the level of significance, we reject the null hypothesis at the 0.02 level of significance. There is sufficient evidence to contradict the claim that at least 5% of batches fail to reach purity standards, and so we can claim that the chemist's claim is actually supported by the data. Right, the chemist is hypothesizing that fewer than 5% of the particular compound have unacceptable levels of impurity, and that is supported. In the sample, 3% of units of the compound did not meet purity standards, which is significantly lower from 5% at the 2% level of significance. Okay, so in this case, the chemist is actually correct in their hypothesis. We can look at one last example here. The researcher is claiming that more than 60% of adults in a certain city support a proposed environmental policy. The survey of 300 randomly selected adults reveals that 195 of them support the policy. We want to test the hypothesis at the 5% level of significance, and we want to use critical values to do so. Okay, so again, we should identify what our hypothesis here. The researcher is claiming that more than 60% of adults support the policy, and so the researcher is making the alternative claim that p is greater than 0.6, right? That is going to correspond to a null hypothesis here of p being less than or equal to 0.6. Okay, and so we have our null and our alternative here. We note that n is going to be 300, x is going to be 195, alpha is 0.05. Okay, and so then we would first want to check, is n times p naught greater than or equal to 5, and n times 1 minus p naught greater than or equal to 5? And if that's the case, then we can proceed with our approximation here, right? In the second part, we're going to actually work out, well, what is our z-score? Okay, and then we want to use critical values here. Now notice that we have a upper tail alternative, and so the z value that we're going to want is going to be z of 1 minus alpha, which in our case is going to be z of 0.95. Okay, and then from here we would compare our z-score to our critical value and proceed. So working out all of those details, we get that the normal approximation actually does apply, right? We're testing h0 p less than or equal to 0.6 versus the one-tail alternative. We have observed a sample size of 300, x is 195, and so that works out to p hat of 0.65. Our z-score is calculated here, filling in all of our details as 1.768. The critical value is z of 1 minus alpha, so that gives us a 1.645. Again, we can get our critical values using our Q-norm function, right? So we want the 95th percentile, and so we take Q-norm of 0.95, okay? That works out to be that 1.645. And so with all of this, we have enough information to actually draw a conclusion here, right? The conclusion is going to be that we reject the null hypothesis, right? Because 1.768 is greater than 1.645. And as a result, there is evidence to contradict the null hypothesis, and we can conclude that more than 60% of people support the amendment, right? So we draw this concluding statement. So since the z-score 1.768 is larger in magnitude than the critical value of 1.645, we reject the null hypothesis at the 5% level of significance. As a result, there is sufficient evidence to contradict the claim that fewer than 60% of adults support the environmental policy, and as such, the researcher's claim is supported by the data. In the sample, 65% of adults supported the policy, which is significantly greater than 60% at a 5% level of significance. All right, so again, we state the evidence, we state what the conclusion of the hypothesis was statistically, and then we make that connection back to the actual scenario that we're dealing with here. So whenever we're dealing with population proportions and we want to draw or make hypotheses test about these, then as long as we have a large enough sample size, the normal approximation to the binomial can be used. And as soon as we're doing that, then we can make use of z-tests for the population proportions. Using the z-tests is helpful because it's going to allow us to just use normal probabilities to calculate all of our p-values, to work out all of our critical values. It becomes a very straightforward scenario to be working in, right? But again, we're still leaning on all of the sort of general hypothesis testing that we're doing, right? We find our test statistic, which in this case is a z-score. We find the null distribution, which is the standard normal here, and then we work out p-values or critical values and draw relevant conclusions there. If we don't have a large enough sample to apply the normal approximation, then we're going to need to turn to alternative procedures, sort of grounded in the general framework of hypothesis testing, in order to test these same types of hypotheses.